So today we're going to be looking at the mean value theorem. And similar to Rolle's theorem, what this states is the fact that if I have two endpoints that create a secant line, and I find the slope between those 2 points, as long as the function is continuous and differentiable, meaning there's no breaks, there's no gaps, and there's no angles, I can find a point along that curve in between those 2 points that has a tangent slope equal to the secant slope. So that might be anything from 1 point to, if I had, let's say these 2 points, one below. If I had something like a sine wave, I might have a more than 1 point, but between these 2 points, I have 2 points that are equivalent to anything that is implicitly defined. If my function, if you could call this a function, it's non-functional, in between those 2 points along its graph, I have 1 and 2, or in between them as such. So let's take a look at applying that. So for number 1, we're asked to sketch a graph using our TI-84. So what I'm going to do is I'm going to pop this over here. Let's zoom out just a bit. And we're going to sketch a graph using this value from -1 to 1. So the first thing that I'm going to do is I'm going to go ahead and clear everything that I've got going on right here. And I'm going to say x to the power of 3 plus 2x plus 2x. Okay, so now that I have that in my calculator, what I'm going to do is I'm going to look and I'm going to set zoom standard and see what the graph looks like. Now I've got a pretty standard graph. I'm only looking at it from -1 to 1. So what I'm going to do is I'm first off going to set it from -2 to 2 and take a peek at that. So now I've got the area that I'm actually defining is right there, but I have a little more context to what's going on. So if I sketch that graph and I say, okay, I get something that looks like this, awesome, and I'm only concerned with from this point to this point, I want to see if there exists a tangent line that goes between those two. Now, assuming that my artistic skills were a little better, what you would notice is that you would have a point up here, and this curve would actually extend down here. And I would have not 1, but 2 tangent lines. So, can the mean value theorem be applied? Yes, it can, because it is both continuous and differentiable, and there will be 2 parallel values. So 2 parallel lines. Because this is both continuous, ignore that, and differentiable. So yes, I would have not 1, but 2 answers because it is continuous and differentiable. If I look at the second one, let's go ahead and graph this real quick. So let's go ahead and set this back to zoom standard. Probably should have cleared my function first and say, okay, x to the value of 2/3. Now I want to look at this from 0 to 1. So I'm going to say, how about from -1 to 2, and I'm going to take a peek at what that function's doing. And I can't see too much about what's going on here, so I'm going to zoom in just a little bit from the top and the bottom, get rid of some of that fluff. So from -1 to about 4. Let's see if that helps clear things up. Yes, it does. So what I see is that the graph actually bounces at a point, which could present problems if that point is included in the interval. And now that point is not quite inside the interval, because it's not within the interval, it's on the edge. So we know that if we had our secant point right there, we would have another one right there, which would be a parallel tangent line. If I scooted that over any further, I wouldn't be able to use the mean value theorem because the function is not differentiable at the point of x equals 0. So for this one, we're going to put a very cautionary yes. We have 1 parallel line because it is both continuous and borderline differentiable. It's my equivalent of saying it's borderline continuous. Or nope, we wouldn't even ignore that. The differentiable meaning at that point right there. So yeah. So why don't you go ahead and try out number 5, pause the video, see if you can't sketch a graph, and say whether or not the mean value theorem can be applied to this one. Okay. So now that you've had a chance to check it out, let's go ahead and see what we're working with here. So I have the sine of x that I'm going to be checking out from 0 to pi. So I want to check my mode. Yep, it's in radians. So I have from 0 to pi. So I'm going to set that from, how about from -1 to, let's say, pi plus 1. I'm going to check that out. My min, I'm going to reset that from -10 to 10. Which we realized it was sine. I have an amplitude of 1. So silly goose. So how about from -2 to 2? That should give us a nice curvy look of what we're dealing with. Okay. So I have a graph that looks something like that. And now I'm only dealing with from 0 to pi. And I know between 0 and pi, I have a flat line. Let's actually move this up here so we're comparing it on equal levels. Which means that between 0 and pi, just like with Rolle's theorem, I know that I'm going to have a tangent line that is parallel to that. But this produced a 0 and that produced a 0, so my equivalent slope is going to be an extrema. So yes, it will give me one parallel line because it is continuous and differentiable. Awesome. So now what that's going to do is that is going to bring us to some applied questions. So let's move over with something like this. And let's take a look at what's going on with these questions. We're going to sketch a graph. We're going to find the secant line and find and graph any tangent lines to f that are parallel to that secant line. So we're no longer going to sketch, we're actually going to evaluate what's going on. So if I take a look at this on the graph, this looks like a rational function. Let's clear that. So I got x divided by x plus 1. And I'm looking at it from -½ to 2. So let's set that from 10 to 10. And so from -½ let's set that to -1. To 2, I'm going to set this to 2.5. So I've got a half variable on each side. Perfect. So I've got a lot of excess space. Let's get rid of that. Let's say, boom. Okay. So what's going on right here? Oop. Curve through that point. Now I'm setting it from half to 2. I want to find a point that goes from here to here. And so visually we can see that yes, there will be some point within that. And we'll have one point. I want to find where that point exists. Probably shouldn't have drawn it right now, but we'll figure it out. So what I first need to find is what is the slope of this secant line? So what I'm going to need to do is I'm going to plug in f of -1/2 and I'm going to plug in f of 2. This will give me my y values from here to here. That way I can start to find slope. So let's go over to a table and let's plug in -1/2 and 2. And so at -1/2 I get a value of -1. 2 I get a value of 2/3. And so we know the formula for slope is going to be the change in y over the change in x. My change in y went from -1 to 2/3, so that went up by 5/3. My change in x went, let's see, from -1/2 to half, that's 5/2. So 5/3 divided by 5/2. Let's see, that's keep, change, flip, that'll be 2/3. I need to find the tangent line that has a slope of 2/3. So how would I find the equation of a line tangent equivalent to 2/3. You guessed it. What I'm going to do is I'm going to push this over, and I'm going to find the derivative of this equation. So I know the top is going to be x and the bottom, let's see, v is going to be x plus 1. I'm going to use a quotient rule to find this derivative. So that's going to be 1, and that is going to be 1. So let's see, my equation I know is going to be low d high minus high d low all over low squared, because we're using quotient. So my low is going to be x plus 1 times d high minus high d low all over low squared. So we get something that looks like that. So let's focus more on this part. So what I get here is I get an x plus 1 minus x all over x plus 1 squared. I'm going to leave that for right now. See if we need to do anything with it. These x's cancel out, so I get 1 over x plus 1 squared. And this is my f prime of x. So I need to figure out when this derivative, can't really see that prime, there we go, when this derivative is equal to my secant slope. So I am just going to set 1 over x plus 1 squared equal to 2/3. And I'm going to solve this equation. Now this equation doesn't look like it's going to be too bad. Let's see, let's cross multiply. So I get a 2x plus 1 squared equals 3. This looks like it's going to end up being a quadratic. So let's see where this takes us. X squared plus 2x plus 1. 2x squared plus 4x plus 2. 2x squared plus 4x minus 1 equals 0. So what I'm seeing here is I see that I'm going to get two possible answers. And if we know what's going on with the graph, we know that this rational function is going to have another slope over here, where I'll have another point tangent, but it's going to be out of our interval, so we're not too worried about that. Okay, so let's set up quadratic formula. We got negative b plus or minus the square root of b squared minus 4ac. So 4 times 2 is 8. So plus 8 all over 2a. So let's check out our two possible answers. Okay. So I'm going to plug in. Let's back out of this. Let's see, negative 4 plus the square root, 16 plus 8 is going to be 24 divided by 4. So my first possible answer is 0.224. Let's see, I'm going to store that as alpha A. Store that as alpha A. Awesome. So my next one is going to be minus. And so I notice my next one is negative 2.224. That one is the one that's going to be out of the interval, because I'm only concerned with values between -1/2 and 2, which that is not. So I can go ahead and I can clear that one out. So I know that at the x value of 0.224, so this is going to be right about right there, is where my tangent slope is going to be located at. And if I wanted to find that point, all I would do is plug in this into my original function. So I could actually theoretically compute what point that is. So I've got my original function. Let's go ahead and take my table and plug in that. So I'm at a point of 0.224, comma, 0.183. I'm truncating this, I'm not rounding it. But realistically, I'm not concerned about the point. I know that I have one value, and that is the x value, where my equation, my tangent line is equivalent to my secant line. Not bad. Let's do one more. So So let's go ahead and draw a sketch of this function. Looking from negative pi to pi of x minus 2 sine x. So it looks like a sine wave along a line. So let's go ahead and clear these out. Let's go ahead and clear this and reset our zoom. So x minus 2 sine of x. So we got it from negative pi to pi. So let's say negative pi minus 1 to pi plus 1. Awesome. So we get a little leeway. Okay. And so that doesn't look too bad. I don't think we need to zoom in on this. Looks like we got shloop, shloop, shloop. And I'm concerned with from negative pi, which is going to be down here, to pi, which is going to be over here. And so what we've got is I have that. And so we can very clearly see on this graph that we're going to have not one, but we're going to have two tangent slopes, one here and one here. They're going to be equivalent to my secant slope. So the first thing I need to do is figure out what is that secant slope, which means I'm going to have to plug in a negative pi and a pi. Let's see what we get. So let's go to our table, and if I plug in a negative pi and a pi. Okay. So for negative pi, I get negative 3.14. Looks like I get a value. I can just go ahead and say this is negative pi. And for this one, I get a positive pi. Not bad. Okay. So I know the secant slope is going to be the change in y over the change in x. My change in y is going to be 2 pi. My change in x is 2 pi. So my slope is 1. I want to find a tangent line where my slope is 1. So how do I do that? You guessed it. I got to find the derivative of that equation. So that just means that with this is a pretty straightforward one. My f prime of x is going to be 1 minus 2 cosine of x. And I need to figure out when that is equal to 1. We'll go ahead and solve for that, which means I subtract 1, so negative 2 cos of x is 0. So when is the cos of x 0? Okay, not bad. So we know the cos of x, if we remember, that is adjacent over hypotenuse. The adjacent is the x over the radius of my unit circle. Okay. So when is the cosine equal to 0? So when is the x 0? That's going to give me a point right here and right here. Okay, so if I'm only dealing with from negative pi to pi, I'm not going all the way around, I'm going forward and backward, which this is going to exist at 90 degrees or at pi over 2 and at negative pi over 2. Boom. Because we know that this is positive pi and this is negative pi from the other direction. So I'm cutting that in half. So I've got pi over 2 and negative pi over 2. Now I could, again, theoretically plug those values in and see what that coordinate would be, but we're not concerned about that. We're concerned about the two values where my tangent lines are equal to my secant line. So having done that, let's take a look at the last one. Now this one's going to be a little tougher. You're not necessarily going to be able to calculate it by hand. So what I want you to keep in mind, even though this one was a little fun to calculate by hand, once you figure out what the derivative is, you're going to need to be able to set that equal to 0. And you're going to use your calculator to find out where that point would be. So keep that in mind as you try number 11. Pause it, take a shot at it, unpause it when you're done, and see how well you did. Okay, so let's take a look. So from 0 to 2, so I'm looking at some sort of positive aspect of this graph. This one looks like it's going to be fun to type in. So let's go ahead and let's clear out our calculator. So I'm going to set this and say 2e to the power of x divided by 4 times the cosine of pi x divided by 4. Oh, I guess we should have adjusted the parameters. But what I do notice is that from 0 to 2, it doesn't sway too much. So I'm probably going to set that from -5 to 5. Okay. So I'm only concerned with from this point to this point, which means that I will have exactly one tangent line somewhere in this neighborhood. So I'm just going to go ahead and, let's say, draw it right here. Okay. So I know that I'm going to have at least one value. I don't exactly know where that one value is, but the first thing I have to do is I have to evaluate what is the slope of my secant line, which means plug in my 0 and plug in my 2. Let's see what that would end up being. Let's plug in a 0 and a 2. Not bad. So 2, 0. So now my slope is the change in y over the change in x. The change in x was 2. The change in y went down 2. So I'm finding a slope of -1. Okay. So where do I find a slope of -1? Well, I need to figure out what the derivative of this is going to be. And this is going to take most of the square. Possibly if you write big, you're going to bleed off a little bit. But I know that this is a product rule. I have u and v. So u is 2e to the x over 4. V is the cosine of pi x over 4. For u prime, I'm going to need to do a subroutine. Let's do that subroutine in green. So if u was x over 4, that would mean u prime is 1/4. F of u would be 2e to the u. So f prime of u would be 2e to the u. So my derivative for this would be 1/4 2e to the x over 4. 2/4, that's going to be 1/2. Perfect. I get that. Okay. Same thing right here. To find the derivative of my v, I'm going to need to do another subroutine. Let's come over here. If I say u is equal to pi x over 4, u prime is pi over 4. F of u would be the cosine of u. So f prime of u would be negative sine. Awesome. So that would be pi over 4. Negative sine of pi over 4x. Awesome. And so because this is the product rule, I take the addition, or I take the sum of these two products. So let's try this out. So I'm going to take half times this. Cosine of pi x over 4 plus this. So pi over 4 times 2, that's going to be pi over 2. Negative pi over 2 e to x over 4 sine of pi over 4 x. And I need to figure out when this is equal to -1. Now, what we've got going on here is that this is not something that we're going to be able to solve by hand. So we're going to kind of cheat our way through this. I'm going to plug this into the calculator, and I'm going to figure out, I'm going to let the calculator tell me when this is going to equal this value. How am I going to do that? Well, I'm going to move everything over, and I'm going to say, okay, let's pull out this 1/2 e to the x over 4. I have cosine of pi x over 4 minus pi sine of pi x over 4 plus 1 is equal to 0. So I'm going to set this equal to y, and I'm going to let the calculator find when this value is at a 0. So let's check that out. So on the graph, wherever that tangent slope is, my derivative is going to equal 0 at that point. So let's go ahead and try our best to type this all in properly. So 1/2 e to the power of x over 4. Get that times the cosine of pi x over 4 minus pi sine pi x over 4 plus 1. Let's graph this. And so what we see is exactly where we expected. That graph of this derivative is going to equal 0, where our derivative would be equal to the slope, because all I did was move that 1 over. And there we go. So I'm going to let the calculator calculate the 0 on this curve. So left bound, right bound, and we're going to guess right about there. Boom, right there. So x is equivalent to 1.016. So 1.016 is where my tangent line is equal to the slope of my secant line. Just like that. And there we go.